Good afternoon, ladies and gentlemen, and welcome to the SAIEE Electrical Insulation Chapter webinar on past, present, and future of SF6 GIS technology in South Africa. Before we start with the webinar considerations, attendees are reminded to ensure the volume is turned up on your device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the Electrical Insulation Chapter playlist. The QR code on the left-hand bottom of the screen is which you can scan and register for the site. It is free. A certificate of attendance will be issued a few weeks after this webinar once we've received the CPD validation number from EXA. I'd like to introduce you now tonight to our host, Prof. Cuthbert Nyamupa, who is the chairperson of the Electrical Insulation Chapter, and he is the head of school and associate professor in the School of Electrical Information at Wits University, Johannesburg. He holds a bachelor's honours degree in electrical engineering from the University of Zimbabwe in '94 and completed his PhD, MSc and postgraduate diploma in higher education at Wits. He received an NRF C2 rating in 2021 for his research on high voltage electrical insulation and the use of nanotechnology for sustainable insulation solutions. He has supervised over 33 postgraduate students and published more than 90 peer-reviewed articles. Over to you, Prof.
Thank you, Means. Yes. Good afternoon, everyone, and a very warm welcome to this webinar on SF6 GIS technologies and alternative gases. I see people are still streaming in, but we will start right away. So on behalf of the South African Institute of Electrical Engineers, particularly the Power and Energy section, I welcome you all to this important webinar. Let me maybe say something about the insulation chapter. So the role of the South African Institute of Electrical Engineering, Electrical Insulation Chapter, is to facilitate sharing of knowledge and experience in electrical insulation engineering technology. And this is for the benefit of all. And it is important to remember that electrical insulation is key for all in the electrical energy ecosystem. It reminds me of a phrase that was termed by Professor Jan Reinders. And by the way, he's passed on recently, and Professor Reinders has a very visible footprint in the insulation technology in South Africa. He passed on whilst he was an emeritus professor in the School of Electrical and Information Engineering here at Wits. So we remember him and we keep the family in our hearts. In his inaugural lecture many years ago, as a professor, he termed electrical insulation as that which keeps electrons in their rightful place. So one can actually argue and say every one of us, whatever electrical energy that we use would have been kept in place. Those electrons that carry the energy have been kept in place by electrical insulation. And talking of electrical insulation, SF6 as an insulating gas is a major part of the electrical insulation system. And in South Africa, the technology of SF6 insulation South Africa was a pioneer in that technology, especially at very high voltages like 765. So South Africa has got huge experience in using SF6 gas. And that's why we have here a presentation from one of the experts in that space, Mr. Fritz Kuhlmann. But SF6 has been declared a greenhouse gas, and therefore there is work to actually replace it with alternative gases. And we are honored to have Professor Christian Frank, who is active in that space and will be sharing developments in the space of alternative gases to SF6. So this webinar will have a presentation from Mr. Fritz Kuhlmann, followed by a presentation from Professor Christian Frank, who is currently at ETH in Switzerland, University of ETH in Switzerland. So to begin the webinar, the presentation with Mr. Fritz Kuhlmann, who has more than 40 years of experience in the power utility, mainly in Eskom, and is currently a consultant, a specialist in GIS. He has a long, rich experience as he joined the workforce as an apprentice and rose all the way to who he is now as a consultant. So without wasting any more time, we hand over to Mr. Frick to take us through the South African experience in SF6 GIS technology. Thank you.
Good afternoon, everybody. I hope everybody can hear me.
Yes, we can. Put your presentation in presentation mode. Thank you, Mr. Kuhlmann.
It's very well.
Perfect. Please
Right, good
proceed.
afternoon. Thank you. Thank you, Professor. And yes, thanks for the opportunity to share with the people from South African Institute of Electrical Engineers my experience in this, and also to contribute to this topic, and hopefully we can contribute to information sharing with you. I was asked to share with you some of the past, the present, and the future as it happened in Eskom, and I will now also use the word NTCSA. That's now the new national transmission, so it's standing for National Transmission Company of South Africa, and I will be sharing with you some background on SF6. When did Eskom enter into the playing field of SF6? Some footprints. Also, I will share some quantities and with you regarding SF6, which we are using in Eskom, just to give you a perspective on how much gas are we talking about. We will also have a quick look about failure modes and what is some of the most common failures in SF6, mainly into the GIS field. And we will also have a look at what is the future in NTCSA regarding the GIS. All right, just to start with for you, I think a lot of these things might be known to you, but it's always good to just have a refresher. And just to go back, and in 1901, SF6 was actually discovered by a person by the name of Henry Moissan and Paul Labau. And they started with the further development, and as early as by the year 2000, about 80% of the industry were using SF6 or sulfur hexafluoride, as it is also known. A thing which is also about SF6 is the fact that it's got an atmospheric lifetime of around 3,200 years. And people, if you take that and you take the last point there of its global warming potential of 23,900 times that of CO2, this is a gas which it's a potent greenhouse gas, but the problem with the biggest problem with this is a gas which is harmful, and that's why it has to be phased out. And therefore, we've got the second presentation where some light will be on that and the way forward regarding that. But also from our side, NTCSA side, also our plans which we have in place to do this. All right. Just a bit of background further. In the year 1938 up to 1951, it was mostly experimental and independent people looking at SF6, how they can use that for the insulation mediums. And then the industrial application started around about 1953, where the first load switches was made. And also, as you can see there, it was between 15 and 161 kV, only 600 amps. And Westinghouse was one of the people on the forefront in doing this. Then it moved further. In 1956, 5 kA circuit breaker, but under 115 kV was also developed. Again, Westinghouse was there. Then it was the puffer type technique, which was developed in 57, 59, the dead tank circuit breakers, which was also the start for the GIS. And then in 1970, they reached the mark of 800 kV or 765 in South Africa terms. And then in 1975, we were able to get into the full spectrum of SF6. Right. When did Eskom enter into the SF6 playing fields? During the time frame 1962 to 75, Eskom entered with the SF6 air insulated circuit breakers in the field of, there is some of them still in existing, but not fully functional, unfortunately. The Dell HP series, the Sprecher and Shoe series, the 300 to 500 series, and also the Galileo. And then in 78, Eskom started with the commissioning of the first GIS. That was by BBC. The first GIS was commissioned on 88 and 275 kV level. That was in Johannesburg, and this is this very same station which is still feeding the stock exchange. So it's playing a very, very important role there. Then in 2012, we went as far as going for the first dead tank circuit breakers, in the sense of this is purely a dead tank circuit breaker. And why I'm mentioning it here, it falls under the family of GIS, and also it also contains quite a lot of SF6. Okay, this is just the indication to you guys to give you some idea what happened in Eskom, or in that stage, or at that stage in Eskom. You can see there that in the year 1978, we started with the 275 at Cracoll, and during 78, 79 up to 1980, it was a constant growth of new stations being commissioned. Johannesburg, Natal, KwaZulu-Natal, Coburg, which we all know, Croydon also in Johannesburg, 81 Drakensberg, that is the peak power station, hydropower station, where this whole GIS setup was built underground, 100 plus minus 120 meters underground. And then we followed through with, and then up to 1981, then there was a bit of a time frame, and then we went to 1987. And in 87, the two 765 kV stations was built, one at Standerton and one at Deelsville, close to Bloemfontein. And those were the two, at that stage, the highest level of GIS stations in the world. At that stage also, Eskom decided not to put all their eggs in one basket, and therefore they decided to, the one station was built by BBC and the other one was built by Toshiba. And both these stations have a very, very good and a very high track level. Then there was a bit of a dead time until we came to the year 2010. And then it's when we came to, we had to start do some expansions and extensions on our stations. And due to the demand which was rising, and therefore there was extensions done in 2010 to Cracoll, 275 and 88. And then we also started with the dead tank circuit breakers in 2010. This circuit breakers was installed on the Cape Corridor to strengthen the Cape Corridor on 765 level. And they are running from ZIAS, which is up in the Standerton area, going down all the way through the Free State, Northern Cape, and eventually end up at Stericus, down a couple of kilometers away from Koeberg on 765 dead tank circuit breakers. This is where the station is made up with AIS equipment, isolators, switches, VT-CTs, but the breaker itself is a dead tank circuit breaker, and as I said, that falls under GIS. Then in excuse me, 2012, Ingula was built, a new a hydro scheme, 400 kV in the Drakensberg, and then our latest one as Koeberg 132 kV. There was an extension there as well, where 2 new feeders was brought into service, and that was done with great success. The whole philosophy in Eskom is that when there is currently an existing substation, if there is extensions to that substation, it is, as we all know, it's treated as a brownfield, and then we do try to keep same with same, because due to the intellectual properties, engineering properties, it's not that easy to join 2 different suppliers. Although it's been done in the industry, at this stage, the way of Eskom is, if it's a new station, it is greenfield, and then we go for new technologies. All right. Sorry, I just had a bit of flu. Then also, when it comes to the footprint of the GIS, in NTCSA, in total, we've got 165 substations. Out of the 165 substations, 153 of them are air-insulated substations. In these substations, there are some SF6 breakers and some SF6 CTs, and they actually contribute to only 19% of the total volume of SF6 used in NTCSA. On the GIS side, we've got 8 substations, and they're contributing to 65% of all SF6 used in Eskom. Dead tank circuit breakers, as I mentioned that to you, that's at 4 stations, contributing to 15%. And that means that in total, Eskom is sitting with 262 tons of SF6 currently in as a footprint. Out of that, 81% is lying in the bin of the GIS, as well as the dead tank circuit breakers. Right, just for interest, this is just a high level of indication to you on what voltage levels we've got the GIS, and also at which is the main suppliers on that. And as you can see, the main suppliers, we are limited only to ABB, or which was BBC, became ABB, which is now Hitachi. We've got the Toshiba on the 765s, then also mostly ABBs, and then on the 275 we've got Merlin and Gerlin, which has now been taken over by Siemens. 132 is mostly dominated by Siemens, and then on the 88 we're back at ABB or BBC, or now Hitachi. People, if there's questions, please put it in the question box so that we will handle that afterwards. That's not a problem. All right, just a bit of to show you, just to show it to you in graphs, because engineering people, we like graphs, and we would rather have a look at a graph or a table, and that will give us the most information. As you can see there, this is just the indication for you to show you that out of the 171 tons of SF6, Beta, the 765 station on its own, got 43.716 ton of SF6, followed by Alpha, which is the other 765. And then as we go around the curve, the graph, it is your Coburgs, it's your Drakensbergs, and then becomes the smaller stations making up the 8 stations which we've got. Then on your dead tank circuit breakers, they just also to give you guys an indication of the amount of SF6 used there. That brings up our 40 tons or 40,000 kgs, 16 ton at Perseus substation, 9 tons, 8 tons, and 6 tons. If we look at that, and those are the, if you just to give it a bit more perspective to that, is also if you look at the number of bays in those stations, we're talking at, if we go to the one for the GIS, if we look at a station like, for instance, Beta, there we're looking at 11 bays. There's only 11 bays, but they're contributing to 43,000 kilograms of SF6. We can go around them. Then it's for Alpha, it's 9 bays, and they carry on until you get to the smaller stations. Fortsburg and Ingulo has only got 2 bays on that. When it comes to the dead tank circuit breakers, respectively, there from the biggest to the smallest, there we've got 7 bays and 4, 4, and 3. So that gives you an indication that for this, only one phase of the breaker, one of the phases of a dead tank circuit breaker has got in the vicinity of 760 kilograms of SF6 gas. So it's quite a lot of gas, taking into consideration the global warming effect of 23,000 tons as 1 kg of CO2. This has quite a big impact on the atmosphere. Right, unfortunately, nothing in life is fail-free, and yes, there is some failures, but we are in South Africa. We've got a fairly good track record on SF6 failures on the GIS, and as I said to you, this is only GIS and dead tank circuit breakers which I've concentrated on, and that was from the day of the first commissioning. We're currently sitting on 73 failures. I will come to the severe failures just now, but this is all the failures in general. As you can see, it's made out of what the biggest part is actually mechanism failures. That's on the mechanism as well as in the interrupter. So it's not purely SF6, but it is falling under this due to the fact that it is SF6 breakers. Defective components and on insulation breakdown, they are heading head to head with 23%, or in total 17 in each of those categories. And your insulation breakdown, that is unfortunately one of the most risky parts of the whole thing about SF6, due to the fact that we're running under high pressure, and also due to the fact that we are in very close proximity between your live and your earth conductors or your enclosures. So that's why that is a very, very insulation breakdown is a very important point. And that's why it is so important to ensure that the quality of the SF6 is monitored on a regular basis, checked and verified, and to make sure that it is within the specs. And that is one of the maintenance aspects as well implemented. And then we've got this green effect here, human errors. Unfortunately, there's always a human factor, and in this case, most of the human errors here is due to either overfilling of equipment or the equipment not utilized correctly, and therefore we had some human error failures as well. But 73 since 1978, I think it's a fairly good rate what we are handling. Some of these are very minor failures, so it's just a trip, and that will count then as a failure depending on the origin for the fault. Then we go to severe failures, and severe failures, there was 30 severe failures, and some of these severe failures is where we actually, unfortunately, had to do with contaminated SF6. And as you all know, SF6 in its pure format, it is harmless it is partly harmless to a human being. You can inhale it and nothing will happen to you. You can, however, due to the density of and the weight of the SF6, .400 kV bushings, there was 4 failures there. Your bus duct failures, but mostly in this case, it is your 275 isolator failures. There were 7 of them. And then on your 765, remember, was the guinea pig in the world, and there were 765. There was a couple of design failures, but they were all sorted out. But these failures happened, and we all know about the bathtub curve and all those things. But these happened in the first part, or the first couple of years when GIS was implemented. All right, people, now we come to our new projects, which we are very excited about. As you can remember, there was quite a time where there was no new projects coming out. And at this stage, we've got 4 projects coming out, all GIS projects. And in the sense that we've got a Mbevu, it's a 400 kV switching station in the Natal area. Philippi, also a station in the Cape, Western Cape, as well as Erika and Weskus-Vleur. Now, Weskus-Vleur is the second Kuburg, and not the generation site, but the NTCSA or the transmission site. That is the station. New station will be called Weskus-Vleur, and that will come just next to Kuburg. And as you can see, we all in the phase of coming to most of these projects are currently out for quotations and out for tenders. And that date on the top there is when we aim to have them. We will start with the commissioning. So yes, there's quite a lot of work coming, and also, but I know that there's a lot of questions regarding are we going to go alternative gas and that. I will answer that question, I think, in my second last slide. Okay, the new technologies. In our case, all our new products will give preference to alternative gas and not SF6. Currently at this stage, the 5 main manufacturers or suppliers up to the voltage level of 132, alternative gas is a possibility and is available. Then in some cases, some of the suppliers are going to 400. 275, not that important in the world. Remember, we are playing in the bigger world, so we have to abide with that, and that's why the 400 kV is also, they're making good progress on the 400 kV, and the first stations on 400 kV alternative gas has just been built, but nothing yet in South Africa, and we hope to be on the forefront on that on our new projects. Then the normal things which is we have gained experience on in the past is things like online partial discharge monitoring, which we're going to implement there, as well as SF6 gas quality and pressure online monitoring, because it is critical to keep your pressure at the desired or the designed level in order to ensure that you don't have insulation breakdown, which will lead to a failure. And then the other part is also we are moving into the philosophy of breaker and a half substation configuration, and that means we're moving away from the traditional double bus bar system with your bus couplers and bus sections. We're going now for a breaker and a half system where you've got the 2 bays interconnected with a tie bay, and that also contributes to a much more reliable and stable network configuration in the case where if you have to lose one of your feeders, and also especially on the GIS side, where it is also it's not that easy to just unplug something and put in something new in there, as due to the construction, as we all know. Right, this is just a bit of a photo album, because I'm seeing I've got about a couple of minutes left. This is just for interest. I don't know, because I don't know the audience, so I don't know who has been to GIS stations and who is familiar with GIS stations. But this is just to give a bit of an indication to you. For instance, here at the top, that is on the 400 kV network, Koeberg substation. This is on Drakensberg. There's two pictures, the one in the middle top and the one right in the center. That's Drakensberg. The thing about Drakensberg substation, although Drakensberg substation has only got 6 bays, but they've got quite a high number of SF6. And one of the reasons for that is the fact that we are transporting the electricity by means of a bus duct from the bottom where it is generated up to the surface level onto the feeders. And those bus ducts, as I said, is there's 6 ducts running up a length of 120 meters. So that is also contributing to a high level of or high amount of gas being used. Then there on the right-hand top, that is the latest from Siemens. Sorry, this was installed at Munich, also in Cape Town. Then on the middle left, we've got one of our substations that is in Vubu in KZN. There you can see the bushings and the bus duct coming out up to the point where you've got your SF6 to air bushings. On the right-hand side, that is Alpha substation. Just a picture giving you the indication of how big this is. But although this is quite a lengthy substation, to think if this was AIS, it would have been 3 times the length and 3 times the width. So that is, as we all know, that is one of the positive factors about the GIS, is that it is much smaller footprint. Then here on the left-hand side bottom, that's good old Koeberg, which has now been received a life extension. The license was granted to them, and therefore we are now going to extend the life of our equipment as well. Then in the middle, dead tank circuit breaker. As you can see, that is the part which I said to you at the bottom part, and that is which is keeping per phase around about 766 kgs of gas. And then the last picture there on the right-hand side is just, it's unfortunately very small, but it's just an indication of a complete GIS bay, consisting out from either a cable end going through your isolators, your CTs, your breaker, onto your bus bars and your isolators on there. So that is from my side, which I wanted to share with you. If there's any questions, please keep that, and we will handle that as we go along. And if there's any questions other than from this, you are more than welcome to contact me, and I will gladly assist you. Thank you very much.
Excellent. Thank you so much, Mr. Frick. That was very insightful presentation, very good overview of what's happening. I mean, I've learned a lot here that Eskom as a power utility is holding around 263 tons of SF6. That's very useful information. And we may all want to reflect that it's not just Eskom. There are other power utilities, municipal power utilities that have SF6 equipment. So I think that's a very important message to take there. And another highlight is the high reliability of SF6 equipment, where you said 73 failures only, 73 out since 1978. And it's also exciting that you considering the new technology, the alternative gases in your new projects. So that's very exciting, and it actually then links us to the next presenter, who is Professor Christian Frank. He is an expert in high voltage engineering. He studied in Germany all the way to PhD, and is currently a full professor at ETH in Switzerland. They have a very vibrant high voltage research program at that university. And he is the convener of a Cigre working group that actually completed work on electric performance of new non-SF6 gases and mixtures, looking across the globe on the developments in that space. And they've published a technical brochure. We are greatly honored to host you, to have you, Frank, Christian, and as you are from Switzerland, you're speaking to the country that holds among the biggest of SF6, and therefore everyone is excited to listen to your presentation on alternative gases. Over to you, Christian. Thank you.
Thanks very much for the kind introduction, and thanks also for giving me the opportunity to present our results. I hope you can see the correct screen now.
Yes,
it's quite visible.
Okay, excellent, good. So as was introduced, I'm happy to present the results from our working group, which actually convened already a few years back. But nonetheless, I think the results are still very important and interesting for you. And I would like to give you an overview on what the group did and what the main outcomes were. So what I'm going to present you is, after a very short introduction about the setup and the members of the group, mostly the content of what we delivered. And yeah, I basically show you three parts in this presentation here. When we started, and that was back in 2017, actually, when the terms of references were written, the goals of the working groups were set to describe methods to identify new insulating gases and gas mixtures. Remember, that was the time where this was very fresh topic, not very fresh, but relatively fresh topic, and not so many solutions were on the market or just coming to the market. So in addition to this, also we were tasked to investigate and summarize the dielectric properties and the practical insulation performance of new non-SF6 insulating gases and gas mixtures for the use in gas insulated systems. And the members were from all over the world, and particularly interesting is the graph on the right-hand side. They came mostly from industry and academia, but we also had representatives from utilities and research and consulting, which kept the balance to always reminded us also to look to the practical aspects and not drift off too much into the theoretical details here. The brochure, this is the final table of content of the brochure. I will not go through it one by one and summarize the 11 chapters. I would like to introduce it basically subdivided into 4 parts. The first part was a summary of the state of the arts, and this is the chapters which are written here in black and are not grayed out. These contain summaries of state of the art. So for example, description of methods to find new gases, methods to characterize gases, and these were methods, let's say, to characterize chemical or physical properties, not so much the electrical properties yet. Part A is, I guess, what you would expect typically of a Cigre working group, to summarize the state of the art and to make an overview, but we went considerably beyond, and because we realized that when summarizing the state of the art, that it was very, very difficult to really make a comparison of the different solutions. And it was at the time where it was not clear which solutions would actually be favored. Utilities were rather unsure of the messages that they got from the different vendors and manufacturers. So actually, we were also thinking about how to make this comparative assessment easier for future work, and kind of, it's not a standard yet, but it's kind of a best practice recommendation. So part B actually was to propose new tests and methods and procedures to compare the insulation performance of different non-SF6 novel alternative gases. Then actually, we even went beyond this recommendation. We already also performed a set of tests, not all of them which we proposed, but quite a few. And I will show you a few results of this. We did a second round-robin test campaign, actually on the gas analysis. The fact is that many of the novel gases contain the strongly insulating component to a very small admixture. And there's certain requirements being made of the mixing percentage uncertainty or accuracy of the filling. And we wanted to see how's the gas mixture analysis up to this specifications. And I would like to give you a short overview on part B and two examples, each one of part C and part D. But let's start with part B, the newly proposed test methods and procedure. And again, as I mentioned before, the motivation was coming from the state-of-the-art analysis, showing that a comparison from one publication comparing or measuring one gas mixture to another publication measuring another gas mixture is not possible because they were using wildly different methods, procedures, geometries, and often important information was missing. Test protocols were not that clearly set as they should have been, which made it more or less impossible. And we wanted to create this foundational work so that really test methods and procedures are defined with which alternative solutions can be compared amongst themselves, but also compared to SF6, of course. And one of the topics was to go beyond the intrinsic insulation performance of these gases, so to look into the practical insulation performance. And with this, we mean the behavior under non-ideal conditions, so non-uniform fields, rough surfaces, large surfaces, also look at PD, partial discharge inception, or non-standard or non-DC or non-AC continuous impulse waveforms, so lightning and switching impulse waveform. And from these measurements then perform limit or determine limits, which are then of use for the manufacturers to ensure reliable design of industrial GIS systems. So the practical tests contained different factors. These were the electric strength for AC and transient voltages, for varying degrees of uniformity, weakly non-uniform fields, but also strongly non-uniform fields, sensitivity to electrode surface conditions, so roughness effects, but also the size, so area effects, under strongly non-uniform configurations, the sensitivity to AC, but then also to lightning impulse relations, and the ratio between AC and LI breakdown strength, so test conversion factors, which are standardized in the IEC standards, for example. I will not go through this table in detail. It just gives you a short introduction to which level of detail actually these electrode configurations in this example have to be specified. So really, they need to be specified and characterized very carefully with respect to gap distances, with respect to degree of uniformities, with respect to surface quality, surface finish, surface roughnesses, and typical pressure range in which the investigation have to take place to be representative for medium voltage and high voltage GIS equipment. And you see the overview here. Of course, the gap distances, ideally, we would have loved to measure in larger gap distances, so more towards industrial standards or what is used in practice. But because we also wanted to perform some of these measurements and the participating test laboratories were limited in voltage, or many of them were limited in maximum voltage application, we had to decrease this gap distance. But the rest was definitely within the range of practical applications which were used for medium and high voltage GIS equipment. So if we look into the different tests, and these tests, the first three ones I will tell you now, those were the ones which the working group was also performing in the round-robin tests. Prerequisite or pre-study was done under uniform field with AC condition, just to make sure how the mixing ratio and the pressure screening is and which range of application we're working at and talking about. And then for the typical weakly and strongly non-uniform configurations, we actually went for these setups here. So we had for medium voltage level, which is typically with a lower degree of uniformity than the high voltage parts, these rod-shaped geometries for the weakly non-uniform configuration with a rough surface. For a strongly non-uniform field, you see the same curvature radius here, but with a protruding tip. And here it's the protruding tip that initiates the breakdown, so the surface here is not that important. For the high voltage, the degree of uniformity is much higher. So the weakly non-uniform field, we actually considered a sphere plane configuration with a certain gap distance. Again, a roughened surface of this sphere, and with a special mounting and a protruding tip if it goes to the strongly non-uniform configuration. So you see this configuration here disassembled. So the tip goes into this holder here, and the holder is then screwed from the back to this sphere to form this shape here. And then this is installed into the test vessel, and tests are performed. There's a large number of 10 additional, or actually 11 additional tests, which were proposed, but not performed within this working group, because that's a large portfolio. And this is also why the development of this switch here and GIS in the non-alternate and non-SF6 gases with the alternative gases is so difficult, because many different situations, configurations, and parameters needs to be studied and to be investigated. This gives you an impression of how many this is. But we went further. It's not only about the electron geometry. We realized in the pre-test that a very detailed description of the experimental setup, the preparation procedure, the execution of the experiment, and the documentation of the procedure is absolutely essential. And we provide a template for the measurement protocol, which can be downloaded here and is available for future use as well. And this is what we recommend to use as a guideline to set up and perform these tests. Then you can be sure that, at least to our knowledge, all the relevant information are documented, which makes then the intercomparison to other experiments of similar type possible. Now, performing these experiments, so the first 3 tests were actually performed. They were performed for different gas mixtures and SF6. So the focus here today is on the perfluoronitrile, the C4F7N gas mixture, because that is of the gas mixtures that we investigated, the one that is most relevant for today's alternative solutions which are on the market. First, if we look into the uniform field configuration, so actually plane-plane configuration, here you see a ratio scan at a fixed pressure. So you see the percentage of C4F7N mixed into CO2, and especially in this very low percentage region, here's a zoom of this, you see that there's a strong non-linear effect, which we call a synergy effect, which makes the increase in electric strength over proportionally strong compared to just a linear interpolation of the mixing ratios. And this is, of course, an advantage because the C4F7N can only be mixed at low percentages due to the boiling point problematic into a background gas of N2 or CO2. And for switching purposes, CO2 is used here. As a reference, with 20% of admixture, you reach the level of SF6 that was measured. And these were performed at 1 bar here. We also did a pressure scan at a fixed percentage, so at 5%. And you can see there's a pretty linear increase with pressure, as we would expect. And at 1 bar, the strength of this 5% mixture is approximately 2/3 of that of the strength of SF6 under uniform configuration. And with 70% overpressure, you reach a similar electric strength level than SF6 at 1 bar. Then we went on to perform the weakly non-uniform and the strongly non-uniform tests under AC and LI conditions. And here it is interesting to note, also here you see the comparison of the gas with SF6. So first of all, you can see that like groups here, this means there is tests from more than one laboratory. And usually we tried to have at least 2, ideally more, of the same tests performed in different laboratories to actually see how intercomparable and trustworthy the test and test procedures that we described are. And you can see this here is a pretty good clustering. So one color is one lab, and the scatter is the uncertainty that you measure from repeat measurements. There is regions where there is stronger differences, but usually the intercomparison is pretty good between the laboratories. And most reassuring, of course, the electric strength of the 5% mixture is weaker than that of SF6. This we know from the pre-tests. But what is important, for example, is that the behavior is very similar. So that means under that weakly non-uniform configuration in SF6, but also in the new gas, the positive lightning impulse breakdown strength is higher than the negative. But for the strongly non-uniform, it's the opposite. There, the positive is the critical. And with this information, you can still work on the most critical part, and you don't have to always perform both tests. You know, the behavior behaves very much like we are used to it from SF6. And with this, like the dimensioning and the performance assessment can go as we know it from the SF6 developments. So as a summary, the breakdown voltages in the mixtures showed similar trends than those in SF6. We didn't see any unexpected effects, and the gas mixtures can also be considered self-restoring. So there was no visible trend of aging, so a deterioration of the breakdown strength with repeated experiments or so. The existing tests and design rules that we know from SF6 can be similarly applied, of course, scaled with the electric strength of the gas mixture. If I then go to part D, which is the second round robin test that we made it for C5 and for C4 gas, but today I focus on the C4 gas only. And again, the motivation for this type of test was the fact that the novel gases, the strongly attaching components, are only admixed with low percentages. You saw the example of 5% in the previous slide, but the vendors give a certain accuracy or precision with which the filling should be done. And the question was, can we fulfill with today's measurement equipment these analyses? So the campaign was structured in a way that we had a gas mixture with 5%, or that was the target, 5% of the novel gas. And this was prepared centrally at one location. Then it was transferred into bottles and shipped in sample bottles. And then it was analyzed in different laboratories around the world, up to 7 laboratories, then investigated sample bottles which came from the same centrally prepared mixture. And the methods that were used were gas chromatography, sometimes coupled with mass spectrometry and FTIR methods. And here you can see the procedure that was applied for the C4 mixture. So it was prepared with a commercial mixing unit at one of the manufacturers. And the composition, the aim was 5%, 90% for C4, O2, and CO2. And then after it was mixed with a mobile analyzer, the mixing ratio was confirmed to be 5.07% and 5.17 for C4 and for O2. Then it was liquefied and transferred into 50-liter shipping bottle, brought onto the site where it was re-evaporated into a 1,000-liter vessel, and then thoroughly mixed, of course, because from the condensation, from the liquefaction, you kind of separate the phases. And strangely, then it was measured to be 5.3% and 5.4% for the C4 O2 mixture. The reason is not known to us, but this mixture then was filled into smaller sample bottles and shipped to the different labs. And these were the test results. So here you see the 7 different labs, and you see the analysis method that was used. And these were measuring values from, I think the lowest one here is 5.23, up to the highest one, 5.57. This is within the mutual uncertainties. So 0.2 plus minus is the uncertainty as given by the labs. But you see there's quite some spread, and most surprising or confusing to us was that we all were above the target value of 5%, which was initially also confirmed after the mixing with a mobile analyzer. So as a summary for this analysis here, the gas analysis within plus minus 0.2% of absolute value is neither trivial nor consistently achievable with today's technology. But we couldn't identify a single root cause for the deviations. What we have discussed was, for example, the calibration procedure. Every lab calibrates their gas chromatograph, their mass spectrometer, their FTIR individually because there's no traceable calibration gases commercially available to date or to the date of this campaign. And they use widely different analysis methods. And there is a certain aspect of sample preparation and shipping, reclamation of the samples, transfer into the different measurement instruments. So these were the root causes which we think are there. But 0.2% seems to be achievable, at least from laboratory standards these days, and for most of the mobile analyzers as well. Good, and with this I come to the conclusion of this small overview, but I don't want to stop without showing you the brochure and basically recommending you to download it and to read it in more detail if you want to, because there's much more information contained than what I have shown. There's a comprehensive summary of the know-how about fluorinated gases to the date of the publication, so that was 22. So the last 3 years, of course, show new developments, but it's still valid what we found there. It is documentation of one of the largest round-robin breakdown test series I'm aware of. It was 14 laboratories that contributed all over the world with more than 270 test series. A complete set of 14 test series was defined, which lays the basis for qualification and comparison of future non-SF6 gases. The experiments were for high voltage and for medium voltage applications. And we have also done measurements, representative measurements on mixtures that were proposed by manufacturers. So the C4 measurement I showed you, there were C5 mixture measurements, there were CF3I measurements and HFO measurements, and of course, comparison to SF6. Despite extreme care that we have taken to create reproducibility in and within one lab and between two labs is relatively difficult and was not always possible to achieve, to our surprise, sometimes even for SF6. So dielectric testing is an art, and not always all the influencing parameters are known to us. Both mixtures, the C4 but also the C5 mixture, show the principal same behavior as SF6. They self-restoring and like the breakdown strengths are quite similar. HFO and CF3I have both been identified as non-self-restoring gases. Sometimes the degradation is so severe that, for example, in the HFO, like carbon fiber bridges were formed, that the breakdown voltage level was basically 0. CF3I left over a very unpleasant stain on the electrodes, which was very difficult to remove. So these are definitely not suitable for high voltage insulation. Further round robin tests were conducted on this gas mixture analysis, not only for the C4 and the C5, but as a key message to take away, the uncertainty of plus minus 0.2% absolute is possible, but not very easily, even under laboratory conditions, and for sure more challenging even under on-site conditions with mobile analyzers. And with this, I would like to thank you for your attention. And as Mr. Schumann also said already, we're here to take more questions from you. Thanks very much.
Thank you so much, Professor Frank. That was quite informative regarding what's happening globally on tests of alternative gases in comparison to SF6. I can't avoid worrying that as South Africa, I don't think we participated in those tests. You can correct me there. And yet,
yes.
oh yeah. And yet, for SF6, what I know for a fact is that South Africa was very active in the development of SF6 technology. So I think on behalf of South Africa colleagues, we are challenged here to participate in the development of the alternative gas technology. Frick presented there that in the new installations, they are looking at alternative gases, and therefore we need to be in that space of research to understand and engage with that technology. So I challenge everyone to come on board on this one. So thanks so much, Frank, for your presentation and sharing. And I hope we'll be able to access that technical brochure and engage with the details in it. So I see a number of questions that have been posed, which means people have really been engaging with the presentation. Is Monte here to take us through that? Otherwise, I will.
No, he's not, Cuthbert. No. You can go ahead.
Okay, colleagues. So if looking at the questions that have been posed, and thanks, colleagues, quite a number of questions there. So there is a question from Vusi Moses Beko. The question is about the quantities of SF6 gas in Eskom, and I'm sure Frick, you presented that, but maybe, and then he's also asking about any experiences with leakages. And related to that question was a question from Mr. Moyo Prince, and it's good to see that you are in this webinar. You then also asked about if there are any specific percentages of leakage cases in Eskom with SF6. I think that would be for Frick. Would you want to take that one?
Yes, sir, I can answer those ones for you. First of all, the question regarding the first one, I think, was about leakages and how do we determine that. And yes, unfortunately, there is some leaks in the equipment. Eskom's got this. We are adhering to our spec to the 0.5% limit of gas leaks, which will be allowed. From our side, we are monitoring on a monthly basis all the top-ups on the GIS. Please, I'm only talking GIS, but we are monitoring all the top-ups. Every single top-up is locked against the compartment, and therefore we will know exactly what amount of SF6 leaked out. The moment we are giving attention to that, and currently we are busy with a drive to cut down on the number of leaks and the amount of gas which we are unfortunately leaking out. And we came up with a new sealing solution, which has been now the past week. And as we spoke, I got the first results today of 100% success on leakage, which we covered at Kuburg substation, where we had quite a large number of gas per month leaking out there. So we have found a workable solution now, and we've got currently at this stage, we've got only 2 stations out of the 8 stations where there is leaks which is too high according to the specs. And both those stations are now actioned with this leaking or sealing procedure, and therefore I'm glad to say that by the end of this year we will cut down on plus minus roughly worked out on 51% of all our leaks in TCSA. Thank you.
Yes, thanks, Frick, for that. It reminds me, I had a discussion with a colleague in the in the United Kingdom, and if I'm not mistaken, he said they are now penalized to top up SF6. I'm not sure what the situation is in South Africa. Would you want to say something about that?
I can only share my knowledge on that. Yes, remember, we're from the technical side, so we are very much worried about that. But there is now new legislation which was brought into South Africa, where we will now get taxed for the use of SF6, and therefore that is why we've got this drive to cut down on all our leaks to the point where we are well within the set limit. Thank you.
Thank you so much. So it emphasizes our need to really be on board with this alternative gas technology. The other questions there's another question from Navin Badasa. He's asking about Eskom's experience with OEMs on equipment on GIS SF6, especially your experience with flying in experts. I think he's talking of from the side of municipal utilities there. So he wants to know what is happening with Eskom. Have you had experiences with difficulties with flying in experts to repair or fix faults with SF6 GIS? Frick.
Lost you there. Just the last bit I got, you say he's talking about people flying in to come and assist. Can you just elaborate a bit on that?
Yes, it's a question about if. Oh, okay, can you hear me? It's a question about whether you have had difficulties with flying in experts from EM or OEMs to fix SF6 repairs. What's your experience in Eskom? I think it's from the utility, municipal utilities side. They want to also learn what your experience has been.
Right, from our side, we are making use of the OEMs. We've got a very good relationship with them, but unfortunately, we must realize that South Africa is not the biggest player in this world regarding this, and therefore the OEMs are struggling just as the big companies like the Eskoms and those companies, that they are also running scarce on skills. But up to now, we made use of twice in the last 6 months with great success and with no problems. It is not perhaps if you want to start for them to start on the Monday, they might start on the Friday, but at least there is solutions to that. But we cannot complain at this stage about the OEMs.
Thank you. The next question is from Edgar Kepps. I think this one, Frank, you would also help. He's wondering, he says his understanding is that the alternative gas equipped GIS is about 40 to 50% more expensive than SF6. How are utilities managing this? And this is also to you, Frank, as you said, for the new installations, you would be considering alternative gases.
Yes, but it is that is also at one stage, right in the beginning, in the early stages, there was mention made that the cost can be as high as double. Now that lately, we also hear that they're talking 40% more expensive. But in the end of the day, that is a business decision which must be taken. If the equipment is technically reliable and technical viable that we can use it, our first preference will be to use the alternative gas. But in the end of the day, that is a business decision which must be taken, and therefore that will be handed to them to make that final decision on that. Thank you.
Thanks, Frank. And Frank, would you want to share any of what is happening elsewhere globally. This is around the fact that the alternative gas GIS is between 40 to 50% more expensive. What are the implications? Frank?
Oh, that's a question to me. Okay.
Yes, do you have anything to add on that from
Well,
Cigre's experience?
From my point of view, or from my experience point of view, which is purely on a technical basis, I cannot say what costs there are. I have not had a single discussion, a single quote or tender joined for this. My discussion with the OEMs is purely on a technical basis, helping them to develop it, make it more compact, more reliable, finding the designs quicker, and so on.
Okay, no, that's fair enough. Thank you so much. There's a question here from thanks to the first presenter. I think I saw a question about whether there's any, or at government level, I think this is Frank, at government level, whether there's any direction or guidance on transition from SF6 technology to alternative gases. Are there any guidance or any legislations or anything from government? Because this would not just be for Eskom, but other power utilities. Would you have any knowledge in that space?
So yes, as I said to you, I know that there is from our environmental department, because that is run by them. There is, we already received that information that there is legislation coming and taxes to be implemented on that, and that is forced down by government. And that's all I can tell you. The detail to that, unfortunately, I am not yet or know of. All we're doing is, and I'm glad Prince Moya is also in this, because he was one of the driving forces when he was with the utility to say, let's move away from this, and that is exactly what we're doing. So we are doing from the technical side everything in our power to get to only make use of alternative gas in the future.
Thank you. Then there's a question.
Maybe at this
yes.
point I can give you the perspective from the European Union point of view. So there is a new regulation on the European Union which clearly states a phase-out plan. So depending on estimations of market availability of different voltage level equipment for medium and high voltage, there's clear dates set where new equipment cannot be SF6 anymore if there's more than one vendor with a non-SF6 solution available on the market. So this is, I think it's starting 28 until 35 is the last phase-out date for the last voltage level.
Okay, no, that's very useful. Thanks so much, Christian. Then there is a question from Gina Donors about the global warming potential of the C4 alternative. Is it completely biodegradable? I think, would you have any answers to that, Christian?
Yes, I do have. Of course, the C4F7N in its pure form is also subject to certain global warming potential. It's in the order of 2,000 some hundred. So it's not zero, for sure not zero, but it's also much lower than that of SF6. And then it is used in small admixtures. So 5% in CO2 or N2 background gas mixtures, so that the effective global warming potential of the gas is lower again, and then very, very small compared to SF6. It's not biodegradable, I think was the question. So it is in contrast to SF6, if SF6 in the arcing is dissociated, so decomposed into its constituents, sulfur and fluorine, it recombines if it is only sulfur and fluorine there to SF6. This is not the case for the C4. So this is dissociated and then converted into other substances upon arcing. But the vendors can dimension the equipment in a way that with the usual lifetime, like number of switching cycles and so on, there's no allowed deterioration of the gas, and the concentration is below the minimum operational one.
Thank you, Christian. I hope that also answers Prince Moyo's question. He had asked, Prof. Frank, thank you for your presentation. Please comment on the concerns of PFAS with respect to C4FN solution. If there are concerns, what is an acceptable solution that is developing?
Yes, I mean the PFAS, so the perfluorinated alkaline substances, they are polyfluorinated. So C4 is one of those substances. I have hard times to imagine that there will be a complete ban of all PFAS substances, because then we would eliminate much of what we use in our daily lives today. But I'm no politician. I cannot see into the future. So there is discussions on, at least on the European Union level, going on with respect to PFAS. But it would be, from a global warming potential point of view, it would be disastrous to not allow the C4 solution, because that basically means everybody would switch back to SF6 for the highest voltage levels, which is for sure nothing that we want. But it's a discussion that is valid and that must be taken. But yeah, it's I think not purely, but mostly political.
Okay, thanks, Frank. There's a question here from Edgar. And I think, I'm looking at this question, also knowing that with organic fuels, in that space of replacing mineral oil with organic fuels, there is a drive to go for retrofilling, where you just fill in with the sustainable material. Is this also applicable? This question from Edgar is also talking about that, to say, the transition to the alternative gases, is it looking at also retrofilling, meaning using the same equipment but now filling with alternative gases? Frank?
Mm-hmm. So yes and no. It very strongly depends on the type of equipment. So whenever there is switching involved, so circuit breakers mostly, then a retrofill is not possible. And this is for technical reasons, because the velocity of sound of SF6 is much lower than that of basically CO2 and CO2 mixtures, which means that the pressure buildup in the breaker is not high enough in the new gases if you just one-to-one replace SF6 with a new gas. So you can't extinguish the arcs then. So this really demands for a new design of the entire breaker chamber, including the drive. If it is for insulation purposes, I am aware of a solution that can retrofill bus ducts from old equipment. The key problem here is that the old ceilings that have been traditionally used, which seal SF6, are permeable to CO2. So these retrofill solutions work, to my knowledge, with C4 and N2. But it's just like these bus ducts, which also Frank explained earlier, like the bus ducts in the substation, which contain a large, up to the dominating amount of SF6 in those substations. So this is possible, yes. And if I may add, because I forgot to mention something, of course, there's also solutions, alternative solutions available which don't use fluorinated compounds. So one vendor offers vacuum circuit breakers combined with high pressure air insulation. And for air insulated switch gear, I know a solution which is purely based on CO2-O2 mixtures, so without the C4 components. So also in this discussion, I think, yeah, one has to mention this if it's about the PFAS and the fluorinated gases.
Okay. Thank you so much. The next one is not a question, it's just information coming from Gina, saying for information, South African carbon tax is currently, that's 2025, 236 rands per ton of CO2 equivalent, and it will increase to 462 rands per ton of CO2 equivalent. So thanks for sharing that information. Just scrolling through the questions, some have been answered, so I may not have to reread them. There's this one, probably you have covered, it's from Daniel Schipper. Would the alternative gas mainly be used in dead circuit breakers? Would this lead to larger DTCBs needing to be designed? If so, so maybe it's related to the retrofilling question. Christian, would you, do you have any additional?
Yes. So if it's in the circuit breaker, I think the current understanding is that the equipment is larger with the alternatives compared to the existing SF6 equipment. I'm sure, I cannot confirm, but I'm sure that vendors are working on making the equipment more compact. It's like with SF6, if you look into the first generation of SF6 circuit breakers that were deployed in the 60s to the solutions that we have today, there is at least a factor of 2 in size, which they're smaller. I don't expect a similar dramatic decrease with the alternative, but it can be expected that they decrease to a certain amount still further. So, but in the moment they're larger, yes.
Okay, and I think this would be more or less the last question, unless I've missed out another one from Udo Chuku. Is asking Christian there. He's saying there are concerns about the byproducts, the toxic byproducts of C4FN and other mixed gas solutions. How true is this? The other question is about retrofilling, which you have addressed.
So yes, for both, for SF6 and for C4 CO2 gas mixtures, after arcing, especially because there is the presence of, like, for example, nozzles which have to ablate to make the pressure build up. There's copper tungsten that carry the arc from the contacts. Maybe there's moisture. So the dissociation products of SF6 and of C4 are toxic. And I think this is known and also written and stated by the vendors. Arced SF6 has to be treated specifically. Maybe here Fred can bring an Eskom experience, but arced SF6, if you evacuate this, has to be treated differently than non-arced, SF6 and C4 mixtures have to be treated differently than fresh. So both contain toxic substances, yes.
Yes, I can just perhaps come, Cuthbert, I can just perhaps quickly come in there. I know we're running out of time. Yes, Professor, you're 100% correct, and therefore there's a total different way of handling contaminated SF6, and that's why it is so important when we've got a severe failure that it is there's a specific process which must be followed due to the toxic byproducts which is formed with SF6. And we've got a process how to do that and how to follow that. Thank you.
Good. So, colleagues, this has been a vibrant discussion, very exciting. As we come to the close, maybe Professor Frank, would you have anything as a closing remark, followed by Frick?
Not really, but I'm very happy to see that utilities are actively and communities are actively looking to replace SF6 and to lower the global warming footprint from our industry. So whatever we can do in this respect, it's I think absolutely necessary, and we should go forward.
Thank you. And Mr. Skuman?
Yes, but from my side, I fully support what Professor said there, and yes, we are trying our utter best to ensure that we are cutting down on the footprint of SF6. with the importance we know what is the importance of that. The only thing is we are a bit governed or a bit restricted by the OEMs because their development is not that rapid as we perhaps would have liked it. But yes, we are surely doing everything in our power to cut down on that. And thank you for the opportunity, and I hope the people learned something from this tonight. Thanks.
No, thank you so much. Maybe my last remarks are to say, I think as South African, that I once had a discussion with Prince on this, that we do need to come back and participate in this space of GIS. We have been very active in SF6, but I think with the alternative gases, we have to come on board. I saw in the chat space there, some colleagues are actually indicating that they would want to participate in research here. The likes of Dr. Andrew Swanson there at University of Stellenbosch has indicated interest in participating in this. So, Christian, we have people in South Africa that would want to come on board in research in this space. So, thank you so much, everyone, for engaging and for actually coming in numbers to this webinar. It's very important. We can't talk of clean energy when that energy, even though we would have generated it from clean sources, but by the time it comes to our point of consumption, it would have been contaminated, if I may say so, by unsustainable material that we would have used in the pipeline. So we will continue engaging. Our next webinar will most likely be on power transformers, particularly looking on the liquid insulation used in power transformers, the mineral oil versus organic oils. So with that, I thank you all, and especially to our presenters all the way from Switzerland. Thank you. We really appreciate you coming down virtually to us here in South Africa. And to Frick, well done, and thank you so much. And colleagues, this is where our webinar ends, and enjoy the rest of the evening until we meet again in the next webinar. Let's keep on adding value to electrical installation. Thank you, and bye-bye.